Welcome back to Lecture 2. In the previous lecture, we discussed how the ideas of taking limits of sequences can be easily generalized to taking limits of functions at plus and minus infinity. The main differences are that, firstly, whereas for sequences our notion of sufficiently late terms has to do with taking the index n very large, for functions at infinity, our notion of sufficiently late terms has to do with taking the magnitude of x very large. So, whereas when working with the sequences, we have to look for natural number indices, for functions we look for real number inputs. Secondly, which is only a concern for taking limits at minus infinity, we see that what is important is not that the value of the input gets large with respect to the standard order of the real line. What is important is that the value of the input gets closer toward the limit. In the case of limits at minus infinity, this gives inputs that are large in absolute value but very negative, and so is quote unquote small in the usual ordering of the real line. In this lecture, we will further generalize this idea. Instead of talking about the limit of a function at plus or minus infinity, we will talk about the limit of a function at a finite point. The basic idea is the same, just that instead of talking about quote sufficiently large unquote input, now we really want to think about it in terms of input values to the function being quote sufficiently close to the target value unquote. The key take-home message is that the circle of ideas behind limits of sequences, limits of functions at infinity, and limits of functions at a finite point are all really the same thing. We are looking at the behavior of a function as it approaches a point, while never quite getting there. Let's get started. Be warned, this lecture is a bit longer due to the examples we will be giving. If you feel comfortable with the basics of taking limits from calculus and college algebra, feel free to play the video at double speed through the first two examples. The third example is a bit more involved and you may want to pay closer attention to. Let's just give the definition right away. While looking at these definitions, you should mentally compare what it says to the infinite limit cases and think about the similarities. Given a function defined on the real line, we say that it has a limit from below at a point A, where in symbols we put a minus superscript next to the A in the limit notation, if for every positive epsilon there is a positive delta, such that on the interval from minus delta to A minus delta to A, the function f is not different from L by more than epsilon. The below and the minus symbol signifies that we are caring about intervals that go from just a bit less than a, the value a minus delta, to exactly a. Notice that we only look at the open interval, so the value a itself is excluded. Similarly, the function has a limit from above at a point a, and in this case, we switch the superscript to a plus in a limit notation if for every positive epsilon there is a delta such that on the interval from a to a plus delta, the function f is not different from L by more than epsilon. In this case, we concentrate on the open interval from a to a bit over a. And finally, we say that the function has a limit at a if it has both a limit from below and a limit from above, and the two values agree. I want to re-emphasize something I mentioned already, that when we compute the limit, we ignore the value of f at a. We consider the values that are almost but still less than a for the limit below. We consider the values that are almost but still greater than a for the limit above, but the value of a never matters. if we redefine the function by changing its value at a while leaving its value everywhere else unchanged, this would not change the limit of the function at a. You can think of this in analogy to what happens at the infinite limit in the infinite limit cases. For sequences, we only ever define terms x sub n where n is a finite number. We never define as part of our sequence the term x sub infinity, because the limit cares about how you approach infinity, but not what infinity is. Similarly, for limits at functions at plus or minus infinity, we never think of infinity as an actual input to the function. We think instead about the behavior of the function as it approaches infinity. And the situation is similar here. For limits of a function at a point a, we don't think about the value of the function at a. We only think about what happens if we move x closer and closer to a. A side effect of this is that for functions that is only defined on an open interval, it makes sense to talk about the limit of the function at one of the endpoints, even though the function is not defined there. So, say a function f is defined on the open interval from 0 to 1. It makes perfect sense to talk about the limit of f from above at 0 and the limit of f from below at 1, since those concepts only require that f is defined for numbers almost but just a bit more than 0 and numbers almost but just a bit of less than 1. Now let's do some examples. The first two are pretty simple, mainly to illustrate our notion and our method of proof. If you feel comfortable with it, feel free to play this at high speed. The function we will consider takes values minus 1 when x is negative, 0 x is 0, and positive 1 when x is positive. I encourage you to draw a picture of what this function looks like for reference as we go through the next couple of slides. For computing a limit from below at 0, I claim that this limit is minus 1. We can notice that regardless of what positive delta I take, for every x in the interval minus delta to 0, this is the interval of numbers just below 0, we see the function f of x is identically minus 1. And so its difference with minus 1 is less than any positive epsilon. So we can say that for any epsilon positive, we can choose our favorite delta, say 1, and conclude that for every x between minus delta and 0, the difference of f of x and minus 1 is less than epsilon. And this shows convergence for f to minus 1 as we approach the 0 from below. For computing the limit from above at 0, I claim the limit is plus 1. The argument is almost the same as the previous case, but let us go through the motions for completeness. For every delta positive, the function is identically 1 on the open interval from 0 to delta. Notice that the fact that we're only using open intervals, which is the same as saying that we're ignoring what happens at 0, is important. If we looked at the interval that included 0, then the statement is no longer true. And so for every epsilon positive, we can choose our favorite delta 1 again and get that every x in the interval from 0 to delta satisfies f of x minus 1 is less than epsilon. And this shows what I claimed. Notice that since f of x is constant on the positive reals and separately constant on the negative reals, in these arguments here, we are in fact used the idea where when asked to prove a for all epsilon there exists delta, it is okay to prove the stronger statement there exists delta that works for all epsilon. To conclude this example, we see that while both the limit from below and the limit from above separately exist, they do give different values. From below we get minus 1, and from above we get plus 1, so the function does not have a limit at 0. Notice that reaching this conclusion does not require us to think about the value of f at 0 at all. What f evaluates at 0 is immaterial for deciding whether it has a limit at 0. Another easy example to reinforce this. Now we're looking at the function that is basically x squared, except that f of 0 is equal to 1. So you probably could already tell me that the limit of f at 0, both from above and below, are equal to 0. Let's just go through the proof to make sure we can do the epsilon delta arguments correctly. For the limit from below, since the function is no longer constant on the negative real line, we have to work a bit more than the previous case. Our delta should not actually depend on epsilon. So for a given positive epsilon, we can choose delta to be the square root of epsilon. Why the square root? It is what turns out to work. Earlier in this semester, we discussed how to choose the capital N to work with a given epsilon when studying limits of sequences. You should do the same sort of prep work when doing limit evaluations. After guessing the limit, you want to simplify the desired conclusion first to help make the choice for delta more apparent. In this case, since the function f of x is equal to x squared for x negative, and we want the difference between f of x and 0 to be less than epsilon, we can compute to see that this is the same as asking for x squared to be less than epsilon, which is the same as asking for x in absolute value to be less than the square root of epsilon, and hence we chose delta to be such. Anyway, based on this, for any x between minus delta and 0, its square is between 0 and delta squared, which proves what we need, that f of x minus 0 is bounded by epsilon on this interval. The exact same argument, changing the interval from minus delta to 0 to positive delta, shows for us that for any epsilon, we can find the delta such that on the interval 0 to delta, the value of f of x is no more than epsilon. Combining the results from the previous two slides, we see that for this function, the limit of f at 0 does in fact exist and equals 0, even though the value of f at 0 is equal to 1. So just to be a broken record one last time, the limit of a function at a point A does not depend on the value of the function at that point A. Now let's do a third example. This time we're going to take f of x to be cosine of 1 over x when x is non-zero and set f of 0 to be 0. Notice that the piecewise definition is more or less required since 1 over x is undefined when x is 0, and so cosine of 1 over x is undefined there. To get a sense of what we're dealing with, it helps to take a look at a plot of this function. Notice that because cosine is always bounded between minus 1 and plus 1, so is our function f of x. What the 1 over x factor does is that as x goes towards 0, 1 over x goes toward infinity, either positively or negatively. And this approach has to be accelerating, since 1 over x is getting to infinity within finite time. This acceleration is reflected in the graph. The apexes of the graph come closer and closer together as we get to where x equals 0. Before x hits 0, the function will actually run through infinitely many up-down oscillations, hitting infinitely many crests and infinitely many troughs. And with this wild behavior, we shouldn't expect there to be a limit for x as x tends to 0. Let's make this idea precise by looking at what happens when we take the limit of f at 0 from above. What we will use is the fact that we know where the crests and the troughs are. When x is equal to 1 over pi times 1 over 2n, where n is a natural number, then 1 over x is equal to 2n pi, and f of x being cosine of 2n pi is equal to 1. Similarly, when x is 1 over pi times 1 over 2n plus 1, where n is a natural number, then 1 over x is equal to an odd multiple of pi, and f of x is equal to minus 1 there. So now we're ready to show that the limit from above does not exist. Before talking about the proof, let's first talk about what we need to prove. For the limit to exist, we need to show that for every epsilon positive, there exists a delta positive such that f on the interval 0 to delta is within epsilon of the limit. For the limit not to exist, we need to show the negation. The statement starting for every epsilon there exists a delta, our negation should say there exists an epsilon such that for every delta, the statement concluding that f of x is within epsilon of the limit for every x in an interval, our negation should say that for any possible choice of limit, f of x is more than epsilon away from it at some x in the interval. Okay, so we're going to start by picking an epsilon. I will choose epsilon to be 1/2. There are many different ones that work, but this one is as good as many. For any delta positive, the interval 0 to delta contains, via the Archimedean property, at least one point that looks like 1 over an even multiple of pi, and at least one point that looks like 1 over an odd multiple of pi. We will conclude that it is not possible for f of x to be within epsilon of any number L on the entire interval from 0 to delta. This is due to an application of the triangle inequality. As we said before, within the interval 0 to delta, there is at least one crest and at least one trough. So knowing that the distance between the crest and the trough is 2, since the crest has height 1 and the trough has height -1, we know using the triangle inequality that the distance from the crest to L plus the distance from the trough to L must be at least 2. This is what the displayed statement says. Since the sum of the two distances is at least 2, it is not possible for both of them to be less than 1/2. So, to summarize, because we know that the function has infinitely many crests near 0 and infinitely many troughs near 0, we know that within the interval from 0 to delta, for any positive delta, there is at least one crest and at least one trough. For any putative limit L of the function, we check that L cannot both be close to the trough and to the crest. And this shows that there can, in fact, be no limit. Just to bring some finality, a similar argument using that the crests and troughs are also piled up in the negative side shows that there also cannot be a limit from below of the function f. And since neither the limit from above nor below exists, the limit without qualifiers also does not exist. We will conclude this discussion with a convenient theorem. If the limit from below of f at the point of A exists, and the limit equals L, then if xn is a sequence that converges to A with every term of x less than A, then the limit of the sequence whose terms are f of x sub n converges to L. You've already used a version of this in Calculus 2, where you said that if a function converges to 0 at infinity, then the sequence with x sub n equals to f of n converges to 0 at infinity. This theorem is very similar. Oh, there we go. Notice that f of x sub n is a sequence. Its terms are f of x1, f of x2, f of x3, and so on. The theorem also holds for limits from above. You will need to change the constraint on x sub n. In the theorem statement, if we only know that f converges to L from below, we only have information on the values of f for x that is almost A but less than A, and hence we require x sub n is less than A. In the case where we have convergence from above, we will change this to requiring x sub n is greater than A. Similarly, if we know that the limit exists on both sides, then all we need is to require that x sub n is not equal to a. This is because, just to emphasize again, that the limit of a function f at a point a does not depend on the value of f at a. So this limit existing tells us nothing about the value of f at a. So our theorem cannot allow the terms of xn to be a, since our hypothesis of convergence gives us zero information there. After all this exposition, the proof is very simple. It is a common technique that you'll be using lots, which may be called proof by passing the buck. Our goal is to show that a sequence f of x sub n converges. We know that f converges as a function and x sub n converges as a sequence. So we will pass what we need, that our task is to pick a capital N given an epsilon and delegate the task to the two known facts. We will use the convergence of the function first. Given epsilon positive, we can find a delta positive such that on the interval from a minus delta to a, the difference f of x minus L is no more than epsilon. The convergence of the function spat out a delta, so let's use that together with the convergence of the sequence x sub n. Given the delta from the first step, there exists some capital N such that for all further indices, x sub n is within the interval from a minus delta to a. This is the statement that x sub n converges to a. Convergence normally only tells us that x sub n is between a minus delta to a plus delta. But in this case, since we already assumed that x sub n is less than a, we can restrict down to the subinterval from a minus delta to a. Putting the two together, we have exactly what we want. Given an epsilon, if we use this n that is guaranteed by step 2, we see that x sub n is within delta of a and less than a, and so f of x sub n is within epsilon of the limit L, and this is precisely what we need to prove to show convergence of the sequence f of x sub n. Alright, sorry about the length of this one. That's it for this lecture. See you next time.